Coming to the protection of carbonyl group. You know, the formation of acetal, hemiacetal are actually used for the protection of the carbonyl group. For example, carbonyl group with this is ethylene glycol, ethane 1,2-diol. Just eliminate water molecule. This way, we can actually protect the carbonyl group in the presence of para-toluene sulfonic acid, PTS. So what PTS, right? This is cyclic acetal or ketol. If aldehyde is used, it's acetal, and if ketone is used, it's ketol. So this process is also used in order to protect the aldehyde group when you have both aldehyde and ketone groups. Look at this. You got aldehyde, you also got ketone. But we know that the aldehydes are more reactive, whereas the ketones are less reactive. Right? Now, suppose if you want to make the ketones react with a particular reagent, no doubt the aldehydes come into picture. I mean, they compete heavily. Okay, if both aldehyde and ketones are there, then aldehydes are going to react with the reagent that you are using. So to make ketones react with that reagent, aldehyde group has to be protected. Okay. So for that sake, we can take methanol. In the presence of dry HCl, we get this is very much free. It can of course react. Okay. So now the aldehyde group is protected. Right. Now the keto group can react. Right. Because aldehyde is more reactive, it is being protected, and the keto group is made to react with the reagent. This is how the formation of acetal or ketol or the carbonyl group protection is done, let us go for the identification test. First of all, test for alcoholic OH. Okay. Now, the first one in this is litmus test. See, alcohols are not that acidic. They are weaker acids. So they have got no action towards litmus. Okay. Now the most important one is steric ammonium nitrate test. Nothing but CAN test. What is CAN? See, this is steric ammonium nitrate. Okay. See, the steric ammonium nitrate with alcohol. NO3 taken forms a pink or red colored complex. Look at this. ROH taken twice. NO3 taken 4 times. Okay. This is a pink colored or red colored complex. Along with this, of course, we get ammonium nitrate. Okay. So the color of the complex here is very important. Steric ammonium nitrate is in fact yellow colored solution. It is an oxidizing agent. Say with alcohols, you get pink or red colored complex. And remember with phenols, we get brown colored complex or greenish brown colored precipitate. With phenols, brown or greenish brown precipitate is formed. Color of the precipitate is very important here. This is with phenols. Okay. Now the distinction of one degree, 2 degree, and 3 degree alcohol. The most important one is Lucas test. See, a mixture of concentrated HCl and anhydrous zinc chloride is called Lucas reagent. Now we know that this reaction proceeds via a more stable carbocation. Right? So that is the reason why when we go for 3 degree alcohol, you know, 3 degree alcohols give turbidity. You can say muddy like precipitate, mud like, or you can also say curdy precipitate, curd like. Give turbidity immediate because they react fast. Because the 3 degree carbocation is most stable. And you know, in this case, we get R3CCl, a precipitate which is insoluble. Okay. Insoluble chloride precipitate is formed readily. Then coming to 2 degree alcohol. So these give turbidity within 5 to 10 minutes. Because a 2 degree carbocation, of course, is stable, but not as stable as 3 degree, right? In this case, we get R2CHCl, insoluble chloride precipitate. Finally, coming to the 3 degree alcohols, sorry, 1 degree alcohol. The primary alcohol give no turbidity at all. Very important. No turbidity because they do not react. Because the primary carbocation is unstable or least stable among these 3 degree, 2 degree, and 1 degree, you know, they give no turbidity. Okay. Coming to the second one, Victor Meyer's test. Meyer. See, with primary alcohols, let us see what happens. A primary alcohol, red phosphorus with iodine, or you can also go with the concentrated HI, but mostly we go with red phosphorus and iodine. Upon which, of course, SN2, we get PI3 in situ when we use red phosphorus and iodine, and of course, iodides are formed. With the silver nitride, we get RCH2NO2. Now, this with the nitrous acid. Of course, this nitrous acid, as we know, is prepared in situ by reacting sodium nitrite with HCl. All right. Now, what happens? Say this OH and this H are eliminated in the form of water, and see what we get. R CNO2 as usual. Then this double bond N, of course, with OH. This, of course, is eliminated. H2 and this oxygen are eliminated, and we get a double bond. Okay. Now, this is called nitrolic acid. This is very important here. Now, this is an acid because of that hydrogen. So I wanted this hydrogen to be there. So you have to keep this OH. Now, this is where the primary alcohols differ from the others. Because of this hydrogen, they react with the bases. Say sodium hydroxide in this case, and we get a salt, RCNO2 double bond NO minus and Na plus. Okay. Now this salt is blood red in color. So the color is very important here. Okay. This is with primary alcohol. Coming to 2-degree alcohol. Almost the same steps, except the last one. Look at what happens. R, CH, R dash, OH. 2-degree. With the red phosphorus and iodine, or concentrated hydrogen iodide. Yes, of course, the same. RCH, R dash, and you get I here. See, with silver nitride, RCH, R dash, NO. Now, take nitrous acid again. Here it is, of course, this water molecule is eliminated this way. Okay. Now we get R, P, then this R dash, you got NO2, and here it is N double bond O, this part. Now, because there is no hydrogen attached to oxygen, as it was in the previous case, this when treated with sodium hydroxide, does not give any reaction. And say this thing what is formed on reacting with nitrous acid is called pseudonitrile. And this pseudonitrile is blue colored. You got red and now it is blue in case of 2-degree alcohol. Okay. Say with 3-degree alcohols, it will be much more condensed. For differentiation sake, you can take them this way also. Now with silver nitrite, this is what. And see when treated with the nitrous acid, you cannot eliminate anything, right? With either OH, you don't have anything to eliminate the carbon. Even with this also, you don't have anything to eliminate. So just no reaction. This is what we say colorless or white. So this reaction is normally remembered as RBC reaction, red, blue, colorless. Red with primary, I mean blood red. Blue with secondary, colorless with tertiary. Okay, very important. Of course, people also call it red, blue, white reaction. No problem. RBC is easy to remember. Just like the red blood cells. Okay. Now coming to dehydrogenation using copper at 300 degrees centigrade. Removal of hydrogen. Let us see what happens with the primary alcohol. See, with primary alcohols, I mean, when they are passed over copper, hot copper at 300 degrees centigrade, they undergo dehydrogenation. Just remove these two. A fresh bond is formed between carbon and oxygen when you remove hydrogen. Okay. So you get aldehyde. So primary alcohols on dehydrogenation give aldehyde. Coming to 2-degree alcohols. When passed over copper at 300 degrees centigrade, same thing, remove a hydrogen. You will get a ketone. If you want, you can take this way. Unsymmetric ketone is what you. Then coming to 3-degree alcohols. Yes, this is interesting. They react in a different way. Now, 3-degree alcohols, rather than undergoing dehydrogenation, you know, they undergo dehydration. Yes. Let me show. This is how a water molecule is eliminated and you'll get alkene. Okay. Alkene by dehydration. So this is special.